Assalamualaikum warahmatullahi wabarakatuh and very good morning to Dr. Asama and all my friends. Today, we are from Group 1. We'll present Chapter 8 entitled Input and Output. I am Nurul Husna binti Mustafa, which will be followed by my group mates, namely Nurul Najwa binti Muhammad Ali, Muhammad Alif Ikhwan bin Zulkifli, Muhammad Izu Ikhwan bin Muhammad Yusuf, and Muhammad Yusuf bin Sumardi. What is an I/O? I/O is input and output function. It will only put out and output after receiving some form of data. So far, we have learned how to connecting to outside world about input and output. The data on which the instruction operate are not necessarily already stored in the memory. Data need to be transferred between processor and outside world like disk, keyboard, and so on. The data are transferred between the memory of a computer in the outside world, which is input and output operation. The rate of output transfer from the computer to the display is much higher. There are two types of input and output devices characterized, which is behavior and data rate. Type of input and output behavior split into three, which is input, output, and storage. While the data rate is how fast can data be transferred. For example, keyboard have 100 bytes per second, disk 13 megabytes per second, and the network have 1 megabytes per second and until 1 gig per second. So the next topic is the program. Control input and output is way of ready character input from keyboard and produce character output on the display screen. Different in speed between processor and input and output device creates the need for mechanism to synchronize the transfer of data. A solution to this problem on output, the processor sends the first character and then wait for a signal from the display that the character has been received. It then sends the second character and so on. Input is sent from the keyboard in a similar way. The processor waits for a signal indicating that a character key has been struck and this its code is available in some buffer register associated with the keyboard. Then the processor proceeds to read the code. There are three programming interfaces, which is memory map first special instructions, asynchronous first synchronous, and the last one is CPU calling first device interrupts. As a CPU needs to communicate with one various memory and input-output device. As we know, data between the process and this device flow with the help of the system bus. Then we have isolate input and output, in which we have common bus, data and address for input and output, and also memory, but separates read and write control line for input and output. So when CPU decode instruction, then if data is for input and output, then it places the address on the address line and set input and output read or write control lines on due to which the data transfer occurs between CPU and input and output. As the address space of memory and input-output is isolated and the name is so. The address for input and output here is called ports. Here, we have different read and write instructions for both input and output and memory. How we know about memory map input and output? In this case, every pass increment due to which the same set of instruction work for a memory and input or output. Hence, we manipulated input and output same as memory and both have some address space, due to which addressing capability of memory becomes less because some part is occupied by the input and output. So that's all from me. This presentation will be continued with my friends Nurul Najwa.
In slide 7, it shows us about transfer timing in input-output. Input-output events generally happen much slower than CPU cycle. There is two types transfer timing in input-output. First, synchronous. Data supply at a fixed, predictable rate. CPU reads or writes every X cycles. Next is asynchronous. data rate less predictable, and CPU must synchronize with device so that it does not miss data or write too quickly. Next slide. Transfer control. Transfer control is who determines when the next data transfer occurs. Pooling. CPU keeps checking status register until new data arrives or device ready for next data. For example, are we there yet? And it will repeat it 3 times. Interrupts. Interrupt is device send a special signal to CPU when new data arrives or device ready for next data. CPU can be performing other tasks instead of pulling device. For example, wake me when we get there. Next slide. Slide 9. LC3. Memory map input output. In table A, I/O register, there is 4 type of I/O register, which is keyboard status rate KBSR, which is the function is bit 15 is 1 when keyboard has received a new character. Next, keyboard data rate KBDR, bit 7 contain the last character type on keyboard. Third, display status register DSR, bit 15 is 1 when device ready to display another chart on screen. The last one is display data register DDR. The function is character written to bit 7 will be displayed on screen. Asynchronous device synchronized through status registers. Pooling and interrupts. The details of interrupts will be discussed in chapter 10. And slide 10, input from keyboard. When a character is typed, its ASCII code is placed in bit 7 of KBDR, which is bits 15 are always 0. The ready bit KBSR is set to 1. Keyboard is disabled. Any type characters will be ignored. When KBDR is read, KBSR is set to 0 and keyboard is enabled.
For basic input routine, first new char. If not, it will repeat to new char again, and this what we call it pooling. But if yes, it will read character. Simple implementation. Memory map input. This paragraph shows the direction of input and output. So, address control logic determines whether MDR is loaded from memory or KBSR or KBDR. For your information, KBDR and KBSR is input. Output to monitor. When monitor is ready to display another character, the ready bit DSR15 is set to 1. When data is written to display data register, DSR15 is set to 0. Character in DDR70 is displayed. Any other character data written to DDR is ignored, while DSR10 is 0. For basic output routine, it will start with screen ready. If not, it will repeat to screen ready again, and this what we call it pooling. But if yes, it will go to right character.
My name is Muhammad Izulikon bin Muhammad Yusuf, and this is the simple implementation on memory map output. So here is the direction of the input and output. So this is the input. DDR control logic is the input, and here is the output. So you can see where the output is going to. Next, keyboard echo routine. Usually input character is also printed to screen. User gets feedback on character type and knows it's okay to type the next character. You can see it here. This the new char. If the answer is yes, going to red character, and if the answer is yes again, it's going to ask if the screen is ready, and if the answer is yes again and the character have been right. And you can see in the box here if you want to more understand about the keyboard echo routine. Next, we're going to interrupt driven input-output. External device can force currently executing program to stop, have the processor satisfy the device needs, and resume the stop program as if nothing happened. And this is because polling consume a lot of cycles, especially for rare event. These cycles can be used for more computation. For example, process previous input while collecting current input. You can see the example in 8.1 in text. Next, we're going to interrupt driven input-output. To implement an interrupt mechanism, we need a way for input-output device to signal the CPU. Then an interesting event has occurred. Second, a way for the CPU to test whether the interrupt signal is set and whether its priority is higher than the current program. And for the generating signal, software sets interrupt enable bit in device register. When ready bit is set and IE bit is set, interrupt is signaled. You can see here, this is the KBSR. This section is for the ready bit, and here section is for the interrupt enable bit, and this is the interrupt signal to processor. Next is the priority. Every instruction execute at the start level of agency. LC3 at priority levels PL0 to PL7. Example, payroll program runs at PL0. Nuclear power correction program runs at PL6. It's okay for PL6 device to interrupt PL0 program, but not the other way around. Priority encoder selects highest priority device compared to current processor priority level and generates interrupt signal.
Assalamualaikum warahmatullahi ta'ala wabarakatuh. My name is Muhammad Yusuf bin Sumardi, and I will to continue this presentation about chapter 8 with testing for interrupt signal. The meaning of testing for interrupt signal is CPU looks at signal between store and feed spaces. And testing for interrupt signal have two choices. If not set, continue with next instruction, and if set, transfer control to interrupt service routine. If you want to understand detail about routine of interrupt service, you can see this flowchart in slide 20. And the next slide show about full implementation of LC3 memory method, input or output. Because of interrupt enable bits, status register KBSR or DSR must be written as well as read. And the next slide show about review question. What is the danger of not testing the DSR before writing data to the screen? And the answer is skip or Gabriel display or provide character. And question 2, what is the danger of not testing the KBSR before reading data from the keyboard? And the answer is could read previous character or even Gabriel data. And the next question, do you think polling is a good approach for other devices such as a disk or a network interface? And the answer is in general no inefficient complex for multiple device blocking. And the last question, what is the advantage of using LDI or STI for accessing device register? And the answer is device address for away from code 9 hit PC offset insufficient, and LD plus LDR requires 2 instructions for each access, and or request an additional register LD once then LDR for each polling attempt. And that's all for me, and thank you.